Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Cassandra Hatcher with us today. Hi, Cassie.
Hi, thank you for inviting me.
Well, thank you so much for agreeing to talk about your really lovely AJ article. We'll get to that in a little bit. It is October 1, 2021 as we record this. I'm in Phoenix. Fall has definitely come to Phoenix. And where are you located? And is it fall yet where you're at, Cassie?
I'm in Lawrence, Kansas, so about an hour west of Kansas City. Today, it seems like fall. It's pretty cloudy today, but all last week was 80s, 90s, so we're kind of in between still.
Yeah, very cool. Good. You look like you're in home office. You got an awesome Oregon license plate over your right shoulder there. Is it?
Yeah, I actually grew up in Kansas. Yeah, I grew up in Kansas, but then moved to Oregon middle school, high school, and was there through my undergrad, then came back to Kansas for my grad school.
Okay, very cool. Very nice. When did you graduate?
Grad school this past May.
Oh, well, congratulations, Dr. Hatcher.
Just master's, but thank you.
I'll still take it. Very cool. Very cool. So Cassie, what do you like to do for research?
I really liked with my master's research, I was working on finding AGN, and that excited me, finding the active galactic nuclei because of the supermassive black holes, and all just seemed big and crazy. And so it was really exciting to me.
Very nice. Very cool. And that is going to bring us to this very lovely article. Where do obscured AGN fit in a galaxy's timeline? And Cassie, take us away.
Yes, first, I'd like to say thank you to my advisor through the 3 years I've worked with her. She was amazing and very helpful, as well as all of our other collaborators, especially Francesca Fornacini. She really helped me figure out how to do the X-ray stacking that we'll be talking about later.
Okay.
So thank you to all of those who helped me. Okay, so starting, the general overlook is that there is a discrepancy between the number of obscured AGN we see in detections and those predicted in simulations. And so we're assuming a lot of them are misidentified as star-forming galaxies. And so what we want is to use multi-wavelength detections to find these obscured AGN that might be misidentified as star-forming galaxies, because often what happens, we'll find one that has an detection in the infrared indicative of AGN, but then its corresponding X-ray detection does not say it's an AGN. So we're trying to pair those to get multi-wavelength confirmation that there is in fact an AGN there. It's just highly obscured sometimes.
Right. Cool. Okay.
So first we can kind of talk about how we got the sample collection a little bit. Let me see what that's. Section 2 near figure 1. So we wanted to look at infrared and X-ray detection because those are some of the most common techniques. Okay. And so in the cosmos field, we first cut back to any galaxy with a mass of 10 to the 9.5 or more, and looked in the redshift range of 0.5 to 3.
Okay.
And that gave us about 110,000 galaxies to look at initially. And then we wanted to find if they had an infrared detection. And we classified that as a galaxy that had a 24 micron detection. And then, so if we look at figure 1, we can just kind of get some population statistics. The blue circle is the galaxies I will be talking about throughout this work. It's everything, we look at everything that has an infrared detection. And then from there on, it's referred to as X-ray detected or X-ray non-detected.
Got it.
And that's what we'll do the stacking on, is on those 11,000 X-ray non-detected galaxies.
Got it.
Comparing them to those about 700 detected galaxies, but they all have that IR detection because we want that multi-wavelength detection.
Right. Okay.
And so let me see.
I'm with you. Very good.
So yeah, those are 2 categories. Next, if we scroll to figure 3, we're using Dr. Kirkpatrick's color selection outlined in her 2013 paper. We break our galaxies into FAGN bins, which is the fraction of mid-IR infrared coming from the AGN. So it's called a FAGN.
Okay.
And we have 4 classifications as the 4 bars. So if we just look at the top panel, the top left, that's
Okay.
the whole population divided into these, the gray being those X-ray non-detected and the teal, the detected. And so our classifications are FAGN of 0, which we know for a fact is a star-forming galaxy because the infrared fraction from the mid-infrared is 0, so there's nothing coming from the AGN.
Right.
0 to 0.3, we call it likely as star-forming galaxy because most likely they're star-forming, but you might have to dig into those individually to kind of pull out it, or if you have a strange signal. From 0.3 to 0.7, we call those composites. So they have characteristics of both star-forming galaxies and AGN. And then from 0.7 to 1, we know those are IR AGNs. So this is our IR classification if a galaxy is an AGN or not.
Got it. Okay. I'm with
And
you.
then the subsequent panels are just increasing redshift, so we can kind of see how our population looks over there. And so next we start to do, well, one of the key points of using this color selection, if we scroll down to figure 4, one of the key points, we started to compare this color selection to other detection techniques, such as the IRAC method in Donnelly 2012.
Here we go.
Figure 4, yes, shows how our color selection technique compares to the constraints of the IRAC technique. And so the black lines you see there, IRAC defines as anything in that little wedge as an FAGN, whereas ours, if you look at the colors,
Okay.
those orange indicate the 0.7 to 1, which is our IRGN, and there's some of those, quite a few outside that wedge. And with those blue, some of those could also are composites. So the key point is that we're finding AGNs outside of those constraints of IRAC because it is quite constrained. So that's one of the key points why we wanted to use this method for our IR classifications.
Nice. Nice. Okay.
And then next,
Okay.
we can talk about the X-ray stacking, which is like the main chunk of my work was doing a lot of stacking. So I'm trying to think of the easy way to explain X-ray stacking. I do have a little animation on a PowerPoint side if you want me to pull that up, kind of visual to show what X-ray stacking is.
Let's do it.
It might be a little easier to explain.
Yeah.
I found it.
Good. Okay, you should be able to share and go right ahead.
Okay, so for X-ray stacking, we use the tool CStack, and the links in the paper is a great tool. And so the concept of the stacking is that it's overlaying images of multiple non-X-ray detected galaxies. So let's say I put into CStack the coordinates or the RA and DEC and the ID number of the galaxy I want. So let's say this is the galaxy I'm looking at. It takes all the pictures of it and it initially gets rid of anything in that picture that we already know has an X-ray detection, leaving any X-ray signals that are unknown where they come from. It does that to all pictures it has of the galaxy that I asked for.
Okay.
And then it overlays them and gives me like a net background count. And so that's what X-ray stacking is. I do that for, we'll call them bins when we get there, of all the different sub bins. And those have, so it stacks each galaxy individually, and then it stacks it with other galaxies as well. So you can pull out an X-ray detection. It's a weighted average, so it'd be over all of those galaxies, but it does start to narrow down. There might be a signal in one of those galaxies, and then from that point on, you can go and get better detections of individual galaxies.
Okay, very nice.
So yeah,
thank you.
Yes, I always like that little animation. It always helped me.
Oh, it makes it very clear. Okay, so we were back here.
Yes.
Big 6.
So go down. Yes, figure 6. So there's a lot here. I will go through it slowly. So first, refresh our FAGN classifications. The green, star-forming galaxy; purple, most likely star-forming; blue, composite; orange, IR AGN. So we have those bins in our stacked galaxies, which is circle. So basically all those galaxies in that initial like Venn diagram that had an IR detection but no X-rays, I now stack them.
Okay.
And I put them all together, divided into these bins to find an X-ray signal for them. I got a count rate, turned it into a flux, turned it into luminosity. And now that's what we have here. The squares are the galaxies that are already X-ray detected. And so I just had to take an average of their luminosities to get these luminosities. And to kind of weed out any biases, just for our sake of making sure our data looked right, we did a combined weighted average of the two, and those are the triangles, but we won't really get into those. So the key points here are, if we look at just the circles in the top left panel, there, first, the star forming circle that has 2640 by it, that's the number of galaxies in it. The important thing is all of our other stacked bins, that purple, blue, and orange circle, are raised above that star forming bin itself. So that indicates there's something going on in those galaxies that are giving it an elevated X-ray luminosity detection.
Okay.
That kind of orange line with the, or red line with the arrow pointed up, that's our 10 to the 42 LX limit. Basically everything about that being kind of say is an X-ray AGN. 2 out of the 3 other points, the purple, blue, and orange, the orange and blue are above that line. The purple is about right on that line, but there's so many galaxies in it, that would be something in the future I'd want to dig into those 7,000 galaxies and maybe bend it up a bit differently to really see, is it above, below, or the kind of distribution in there. And if you think, as we go on the x-axis and we increase FAGN, we're expecting to find more AGNs. And then on the y-axis, as you increase luminosity in the X-ray, you're expected to find more AGN as well. So we see a correlation between increased AGN, increase FAGN, increase X-ray luminosity, which is great. And then also the really key point is they're all below their corresponding squares. So the corresponding X-ray detected galaxies, also those bins. So it's showing that they're still having an elevated limit, but they're below the already X-ray detected one. So that's might be why they didn't get detected in X-rays in the first place. But by stacking them, we can actually pull out that there is a signal there, and we need to do more investigation.
Okay.
And then subsequent kernels are increased, or extra divided into redshift bins of 0.5. And again, as one of the key points, just as we looked at the redshift, as redshift increases, we also see an increase in the LX of the stacked bins, which is interesting.
Yes. And the trend still holds.
So that is one of the first signs that we were getting, that doing X-ray stacking is finding some low luminosity, if not obscured AGN, and we are able to use X-ray stacking to pull out these galaxies.
Nice.
So next, we looked into the possible obscuration of these galaxies, and that would be figure 9.
Okay.
And so for obscuration,
oops, where did I go here? Here we go.
Yes, we use a relation, the IR infrared luminosity divided by the X-ray luminosity. And if it was greater than 20, we defined it as obscured, as Chang did in their 2017 paper, because we're trying to compare. And they explain why they chose 20, but we'll just say we chose 20 to match their paper and compare.
Okay.
So again, this paper, the top left panel is the whole galaxy, then subsequent by redshift. So we'll just focus on the top left. X-axis is your AGN infrared luminosity. Y-axis again is X-ray luminosity. The gray behind it is all the galaxies in the cosmos field that I'm looking at plotted on there. And again, those colors are stacked bins. The yellow obscured line, anything below it, we say is obscured. And then again, the AGN line, anything above it, we say AGN. So I kind of call that my obscuration triangle. Anything in there is an obscured AGN. Is that we're hoping. So as you can see, 2 out of those 3 points are obscured AGN, most likely based on this diagnostic. And again, that purple point, even with the error bars, it's always right near the limits of both. So that's a point I'd want to dig into in the future and kind of separate those galaxies a bit more.
Okay.
And what's great here is that if you look at where those points are in relation to those gray cosmos points, is that with X-ray stacking, we're actually pulling data from an area that's not really looked at yet. Like all that white area is places we don't have data yet, and we're right on the edge of current cosmos data, and we're kind of getting down to here with the X-ray stacking. So we're able to probe a regime that isn't currently probed with the current X-ray surveys because the detection limits are just so low. So you have to pull in the stacking to actually get those. And then again, as we increase with redshift with each panel, we're seeing an increase with LX as redshift increases again, like we saw back in figure 6. And it's highlighting even more and more that we're pulling data from a regime that doesn't currently have data in our surveys. So that's also really exciting that even though if you don't have specific data, you can find data and you can get it accurately.
Okay. Okay, I'm with you. Cool.
So let's see, next key point. So then we can kind of move on to the discussion. We're going to skip, actually, I'm going to skip down to figure 13 because this is when we start looking at where it might lie in a galaxy's timeline, which is the whole question I asked at the beginning, right, with my title.
Right.
So what we did here is that we did all of our stacking and we're finding low luminosity, possibly obscured AGN, and we've been comparing them to our X-ray detected AGN and galaxies in the bins. And now we want to see where they hit on the galaxy's timeline. So we looked at the galaxy's main sequence. And for that, we're looking at the relationship between the stellar mass and the star formation rate.
Okay.
And so those are the equations. So again, the gray in the background is the cosmos field as a whole. The colors are colors are the FAGN bins. They have now additionally been divided into high mass and low mass. The open circles are low mass, 9.5 to 11, and the solid are 11 to 12. Additionally, instead of doing the X-rays in those bins as well as we just did a full one of the X-ray AGNs, it's just that pink square instead of also divided by FAGN, because we know that they are X-ray AGN. They were all above the X-ray line. The lines are the main sequence. The dashed lines are the 3 Dex errors. As you can see, they change color per redshift panel, except after 1.5 up to all the way to 3. That's because the cosmos field doesn't actually evolve that much towards a higher redshift. So we use the same main sequence line for higher redshift past 1.5.
Got it. Okay, thank you.
So let me go to my key points. I had them written down. I want to make sure I hit these because these are the exciting things, right? Yes. Okay. So we see that they all lie, besides that blue and orange one in that first panel, they all lie, the X-ray AGN and our predicted IR X-ray AGNs, our stacked ones, lie within 3 Dex of the main sequence.
Yes.
Those 2 little ones. So those are some ones you'd want to look into and be like, what's going on there? What's very important is that they are really indistinguishable from these X-ray AGNs. Those square points are at the same spot as all of our stacked, are most likely obscured low luminosity AGNs. So this kind of argues against the idea that X-ray detected AGN are only found in a special phase of a galaxy's lifetime, right before quenching, because we're finding the obscured AGN are also there at the same time because they're indistinguishable. And so our results with this support the picture that star formation and AGN luminosity are not tied together in any particular way from these stacking analyses. And so overall, the main conclusions we got from this work and from those main key figures is that 1, stacking is able to reveal low luminosity AGN as well as possibly obscured AGN that are currently undetected or maybe misidentified as a star-forming galaxy. Stacked bins with an FAGN less than 0.3 are appearing to host low luminosity AGN. Oh, sorry, that was a hardness ratio plot we didn't get into. That was a whole another rabbit hole we went down at the end, so we'll skip past that one. Obscured AGN are found in galaxies where star formation is still ongoing, and X-ray stacked AGN are indistinguishable from those X-ray detected AGN on the main sequence at that plot we just looked at there, right there. So it argues against that. There's something special about X-ray detected AGN in terms of a galaxy's life cycle. And we can do one more little plot. We made a toy evolution model to kind of play with if we can estimate in the future how long AGN stays in particular phases. So if we go to figure 11, we made a lot of assumptions for this. It was kind of just curiosity of ours. We made the assumption that our sources are all drawn from the same population,
Okay.
but they're just in different evolutionary stages. So we can use information from our stacking plot, that's figure 6 with all of our stacking and all the points and the panels,
Okay.
to see where they might be. So basically we could put, based on all of our assumptions, we could get the percentage of time if we, sorry, back up side. If we assume it goes from an FAGN of 0 to 0.3 into the 0.3 to 0.7 bin, and then into the point, like if we assume that's how it evolves, if we take the percentage of each galaxy that's in that bin classified, we can say that's the percentage of its lifetime that we're seeing. So that was our assumptions, our toy model.
Okay.
And that's kind of what's laid out here. The solid bars are the lifetimes for the detected galaxies, or the stacked galaxies, and the hashed is the detected.
Okay.
And we only look all redshift 1.5 to 3 because below that, not everything was classified as AGN. It didn't have high enough luminosity.
Right.
So this kind of has shown us that an AGN spends most of its time in the 0 to 0.3 phase, both detected and stacked. So both obscured or unobscured, it's mainly spending it in a very low IR luminosity phase.
Okay.
But as it increases in redshift, this phase decreases, and then that blue middle phase of 0.3 to 7, the composite phase, increases. So there's just kind of a toy model we just try to play around with, see what's going on, and we thought it was kind of interesting to see that they had similar trends despite being detected or stacked. And so that was kind of our last conclusion, that AGN, regardless, at all different redshifts, spend the largest portion of their life in the less than 0.3 FAGN phase. Cool. And lastly, we found that analysis of that it may be increasing redshift. Sorry, then combination of obscuration and the toy obscuration plot and the toy model plot suggests that the fraction of time an AGN spends in its obscured phase may increase with redshift as well.
Nice. Nice. Cassie, thank you so much for walking us through your very lovely AJ article.
Thank you again for inviting me. And thank you to all my co-authors who helped me figure all this stuff out.
Awesome. You touched on it a couple of times. Things to follow up on. So where do you think the community can go over, let's say, the next 3-5 years to help tighten up some of these trends, or gather other additional data, or generalize? Is it stuff that, for example, Vera Rubin Observatory could take a look at? Is it something JWST, you need kind of that kind of stuff? Where do we go?
I know initially when we had started this, I was going to look in the GOODS South and a couple other fields, but when it came to data and all that, Cosmos was the most comprehensive for us at the time. I know that part of my work has been passed on to an undergrad. She's going to start looking in the GOODS South field, so you can do the same analysis in another field already. But when it comes to even more specific data, especially like with that purple point, I kept telling us, like, it's always near the threshold. JWST and higher, more accurate telescopes have to come in and get more information. But an analysis like this, you can narrow it down to those 7,000 galaxies and be like, I need to look at these, as opposed to, we have these 10,000 that have no x-rays. Like, this can at least get you to narrow down what you need to look at more and what you need to get more specific data on.
Target selection.
Yes.
Very cool. All right. Well, I look forward to seeing some refinement of this work over the next couple of years as we figure out those obscurations or not in these AGNs. So very cool. And that'll do. And I hope this made your astronomy day just a little bit better, everyone. And we will see you on the next one. Bye-bye.